Welcome students. Today we'll look into a problem from JEE 2025 paper 1. The reason for taking this problem is to show you how a simple problem becomes complicated during the exam time. Okay, so this is a very simple problem. Yeah, there is some bit of calculations in it. The only point I'm trying to make is if you look at the data provided by the JEE 2025 reports, it says that around 60% of them even didn't attempt it. That means 40% attempted. Out of those 40%, around 11% got it completely wrong. That means none of the options were correct. And out of those, 24% around students got it partially correct. That means all options that were required to be checked were not checked. Only around 5.26% of the students got it absolutely right. So around 1.8 lakh students and only 5% got it right. The majority of students got it wrong because of three things. First is just by looking at the figure, they got confused and they didn't attempt. Second, they actually oversimplified the problem and applied some of the things which are not applicable. Third, they didn't verify all the options correct. And we'll look into all the three problems. One is just the image itself, but we'll talk about where the other two mistakes are. Okay, so let's look into the problem. So the image is there in the question itself. I have actually simplified it and I have made the y and x axis on the plane of paper. And you can see that the B is coming outwards towards the Z direction. This is a square loop of side L with resistance R and mass M is actually trying to enter the magnetic field zone. The initial velocity at time t equal to 0 was V naught. So it starts entering and I have made a black dotted line which is at time instant t. The velocity is again Vj in positive y direction and there will be some actions happening here. So what are the actions? That means there is first, there is a change of flux that is happening. Second, if there is a change of flux, there is current. If there is current, there is force. If there is force, we need to see whether the force is balanced or not. And if it is not, then there will be some acceleration or deceleration, right? And we have four options. So just by looking at it, we can simply say that the option B is correct. Okay, why so? Let's say it has completely moved inside the magnetic field, the loop, right? What happens if the loop is completely inside a uniform magnetic field? That means even if it moves further or stops, there is no change in flux. If there is no change in magnetic flux, that means there is no potential difference. If there is no potential difference, there is no current. If there is no current, there is no force. Makes sense? So just by looking at the problem and reading the problem, we can say option B is correct. Okay. Now let's see whether the rest of the three options A, C and D are correct or not. But before that, let's actually see what's happening and let's try to come up with some equations. There is one more information that is provided here is actually a constant is given here, which is K is equal to B naught square L square by M into R. And we'll see how we can use it because most of the options provided are based on velocity with reference to this K value. So first and foremost, what is the change of flux that happens when it actually enters a magnetic field? The change of flux is what? Let's calculate this simple area. What is this delta P is B naught. And what is the change in the area? Change in the area can be written as L into Y because this Y is the distance that is moving at any point of time and that time is t. What is the change in flux with respect to time? Is equal to B naught L, and because Y is changing and the rate of change of position of Y is equal to what? Is the velocity at that instant. So we can simply say dy by dt or we can say B naught L V. This is not V naught, by the way. This is V at any time. Okay. What is this d phi by dt? This gives us a potential, and that means this epsilon is equal to V naught LP. Now, a potential is set up around this loop at any instant, and the value is given with V naught LP. So, how do we calculate the current? Because R is given, I can simply say IR equal to V naught LP, or I is equal to V naught LP by. So, first equation I got for the current. Why I need to go to current? Because if I don't get the value of current, how will I calculate the force? So, if the flux is outwards, that means there is opposite direction, there will be an EMF generated. So, for opposite direction of EMF, the current needs to move in which direction? It has to move in this direction, right? Okay. So, the I is this direction. Now, as we know that because this force and this are opposite, these two arms, the current is opposite. That means the force that will be developed by these vertical arms will be always net force will be zero. So, let's not consider it at all. Let's talk about this arm. When this arm, the current is in this direction, B is outwards. What will be the direction of the force with right hand rule? Right, it will be downwards. So force is downwards. That means once we push it with a velocity, it will start decelerating, because that is the only active force in this arm. In this arm, there will be no force because it has not yet entered the magnetic. So because this force is working, what is the formula of force? Force for a current carrying conductor in a magnetic field, BIL. Everything is 90 degrees, so we don't have to worry. We can simply say BIL. Now we have I as well here. From here, we'll apply the value and we'll say V naught square L square V by R. So we got the force value. And there is a constant which has been given. If you move M near K, you will see that V naught square L square by R is this value. So I can simply say F is nothing but N times K times V. So if I have the force, now what? So I will have a acceleration. In this case, it's a deceleration. So what is the value of A? Value of A is divided by M. So we will get it kV, and the direction is negative if I take it vector wise. Okay, great. Now if we have this value A, how can I, because if you look at the options, it asks you for time, it's asked you for position. So two things we need to know, that and what is given, we have been provided with velocity. That means we need to find two equations which can relate me with velocity and time and velocity and position. So how do we do it? We have to use this A. Now, this is where the first mistake happens. What is the first mistake? This acceleration is a non-uniform acceleration. Most of the students who got it wrong is because they tried the linear equations of motion from kinematics. Those equations are only applicable for constant acceleration and not for variable acceleration. So you cannot use that. That's the first mistake you have done. So now let's see. So my acceleration is equal to minus kV. I can write it in the form of dv by dt is equal to minus k times v, or I can say dv by v is equal to minus k times dt. If I integrate it from which perspective? 0 to time t, and what was my initial velocity? V naught to v. So my equation, actually if you solve this, this is a very simple equation where I get t is equal to 1 by k times ln of v naught by. So this is one equation I got, which is time versus velocity. So this can actually look into some of the options. What are the other things that we need? Same equation let's take, and can we write this equation as dv by dt is equal to minus k dx by dt. So I can also write dv is equal to minus k times, sorry, this is a capital K, dx. So again, if I integrate it v naught to v and again integrate 0 to t, what I'll get? I'll get v minus v naught is equal to minus k times t. Sorry, not t, x. Sorry, I should not say x, I should use y because I've used y as a direction. So this is one equation and this is second equation. Now let's see how can I actually use these two equations and look at all the three options. So what is given in first option? First option says if my velocity is v equal to v naught equal to 1.5 kl, that means it will stop before it enters the magnetic field completely. So let's see that. Let me use, because position it's talking about and velocity is given to me, so I'll use this equation. My equation is v naught, sorry, v minus v naught equal to minus of k y. What is v when it completely stops? It stops at 0. What is my initial velocity? Minus 1.5 kl. What is the distance that it should travel? I can calculate that it comes around 1.5 L. That means the first option is incorrect because body or the loop will actually travel 1.5 times L and not anything less than L. If it was less than L, I would have said yes. Okay, the answer is correct, but it is. So first option A rejected. Next, look at the second option, which is the third option in my case, because B is already, we have said it's correct. So the third option says that my V naught is equal to KL by 10 and it should stop at 1 by K times ln of 5 by 2. Let's look into it. So if it has to stop at this time, let's see what is the distance it travels. So again, applying this, final velocity is 0 minus V naught, which is equal to KL by 10. What is the distance it travels? Whether it stops or not, y comes around L by 10. Okay, so this time it could not enter it completely. It has only traveled 1/10 of its side length. That means it stops. Now, the second part, which most of the students might have made the mistake, because it stops, they might have actually corrected the option. But we have to check whether the value is the same or not. Okay. So now let's take the time versus velocity. What happens when v is equal to 0 in this equation? If this v is equal to 0, that means this becomes infinity. Log of infinity is what? Log of infinity is infinity. That means time it takes to stop is infinity, which is not the same as the value given. So option is incorrect. Okay. But let's think about it. How it can happen that it stops at L by 10th distance and it takes infinite time? The reason is this is an exponential function. It's an exponential decay. So we know how exponential decay works, right? This is t and this is velocity. So for velocity to be a 0, t has to go infinite. So this is an exponential graph which actually shows an exponential decay of v versus time. So yes, it travels L by 10 distance, but it takes forever. That means it slows down further, slows down further, slows down further, and it takes a lot of time to actually achieve Z. Got it. So even if first part is correct of the option B, second part is incorrect. Okay. So till now only the option that we got correct is option B. Now let's verify the last option. What does the last option says? It says that if I have given a velocity of 3 times kl. That means the body actually enters completely inside the magnetic field exactly at some time. That means it has given us y this time, which is equal to f. That means if this body completely moves here, it will travel length L. So we can calculate the velocity at that time using this below equation. So V minus 3kl is equal to minus k. Y is what? L. So V is equal to 2kl. So this will be the velocity when the body just enters the magnetic field completely. If our velocity is given as this. Now let's say whether the time is the same or not. So for time to be calculated, we have this, right? So what is V? This is 2kl, and what is V naught? That is 3kl. So based on that, we say 3kl divided by 2kl, which is equal to 1 by k ln 3 by 2, and that is the option, right? So the two mistakes that we majorly do when we start a problem, we might have actually wrongly applied the linear equation of motion from kinetics. And the second problem is that in option C, we just checked the first part, we never checked the second part. We thought, yeah, it might be correct. So never make that mistake. Always verify whatever is provided to you. Okay? Thank you.